Imagine a system handling data. Now picture this system not confined to one computer, but spread across many. That's a distributed system in a nutshell. Each component operates independently, yet they work together. This setup offers incredible power and flexibility for handling large-scale tasks. Think of a symphony orchestra. Each musician plays a unique instrument, creating a harmonious whole. Similarly, in a distributed system, each computer contributes to the overall goal. This collaboration enables efficient processing and data management. Distributed systems are becoming increasingly common. They power many online services we use daily, often without even realizing it. From cloud storage to online gaming, these systems are the backbone of the modern internet. Let's break down these terms. In a centralized system, one central authority controls everything. Think of a kingdom with a single ruler. Decentralized systems distribute control among multiple entities, like a federation of states. Now, distributed systems take decentralization a step further. They not only distribute control, but also data and processing across multiple nodes. It's like a global network of collaborators, each contributing to the collective knowledge. The key distinction lies in the level of interdependence. In decentralized systems, entities can often operate independently. However, in distributed systems, components rely on each other to function correctly. The line between decentralized and distributed can be blurry. Imagine a network of libraries. Each library is independent, decentralized, but they share a catalog for borrowing books, distributed. This example highlights a crucial point. Systems can exhibit both characteristics. The defining factor is the level of interdependence and data sharing. When components heavily rely on each other and share data seamlessly, you're likely dealing with a distributed system. Understanding this distinction is crucial. It helps us appreciate the complexity and power of distributed systems. They represent a paradigm shift in how we design and build applications. Some believe centralized systems are simpler and more efficient. While they offer advantages in specific contexts, this isn't universally true. Centralized systems can be prone to single points of failure. If the central hub goes down, the entire system collapses. Distributed systems, on the other hand, offer redundancy. If one node fails, others can pick up the slack. This resilience makes them ideal for critical applications where downtime is unacceptable. Moreover, distributed systems can scale horizontally, adding more nodes as needed. This flexibility allows them to handle massive amounts of data and traffic, something centralized systems struggle with. Section 5. The many faces of distributed systems. Distributed systems come in various flavors, each with its strengths and weaknesses. Client-server architectures, like email systems, involve clients requesting services from a central server. Peer-to-peer networks, like file-sharing applications, distribute data and processing equally among all participants. Cloud computing platforms, such as Amazon Web Services and Google Cloud, represent a complex form of distributed system. They offer a vast pool of resources, dynamically allocated based on demand. This flexibility has revolutionized how businesses operate. Understanding these different architectures is crucial for choosing the right solution for a particular task. Each type presents unique challenges and opportunities, requiring careful consideration during the design phase. Section 6. Designing for success goals of distributed systems. Designing distributed systems comes with unique challenges. One primary goal is transparency. Ideally, users should interact with the system as if it were a single, unified entity, oblivious to the complex network behind the scenes. Another crucial goal is resource sharing. Distributed systems excel at pooling resources, making them available to all connected devices. This efficient utilization maximizes resource utilization and reduces costs. Furthermore, these systems are designed for scalability. As demand grows, new nodes can be added seamlessly, ensuring performance remains consistent even under heavy load. This adaptability is a key advantage in today's dynamic digital landscape. Section 7. Openness and flexibility. The keys to adaptation. Openness is another vital aspect of distributed systems. Open standards and protocols allow different components potentially developed by different teams or organizations to communicate and interoperate seamlessly. This interoperability fosters innovation. Developers can build upon existing systems, extending their functionality without reinventing the wheel. It's like adding new modules to a Lego structure, promoting rapid prototyping and development. The separation of policies and mechanisms further enhances flexibility. Policies dictate how the system behaves, while mechanisms define the underlying implementation. This separation allows for easy modification of policies without disrupting the entire system. Section 8, the pillars of trust, dependability and security. Building trust in distributed systems is paramount. Dependability ensures the system behaves as expected, even in the face of failures. Redundancy, fault tolerance, and self-healing mechanisms are crucial for achieving this reliability. Security is equally important. With data distributed across multiple nodes, protecting sensitive information from unauthorized access becomes complex. Encryption, authentication, and authorization mechanisms are essential to safeguard data integrity and privacy. Designing secure and dependable distributed systems requires careful consideration of potential vulnerabilities and attack vectors. Robust security measures are not just an afterthought, but an integral part of the system's architecture. Section 9, scaling up handling growth in distributed systems. Scalability is a defining characteristic of successful distributed systems. As the number of users, data volume, or processing demands increase, the system should handle this growth gracefully without compromising performance. Horizontal scaling, achieved by adding more nodes to the network, is a common approach. This distribution of load ensures that no single node becomes overwhelmed, maintaining responsiveness even under heavy traffic. Effective load balancing mechanisms are crucial for distributing traffic efficiently across available nodes. These mechanisms ensure that no single node becomes a bottleneck, maximizing resource utilization and optimizing performance.